tape it?
Yeah, I got it. And I'm recording.
Alright, so we're the Baja Vehicle Validation Team, and this is our senior design project, and it's for winter 2015 quarter. I'm John Goldsmith. I'm doing the introduction and the conclusion. This is John Ford doing the drop test. We've got Isaac doing the accelerometers and some of the lab view. Jake is going to be doing the data analysis, and Eric's going to be working on SolidWorks. So basically the scope and task of the whole project here was to do a test bed where we can design, well, we're going to design a test bed so we can measure the forces that we're going to be inputting into the vehicle and get an idea of what the vehicle is going to be seeing on the actual courses for the Baja test. And we want to do this so we don't run into these kinds of issues where we break our control arms or break the kingpins. So the phase 1 deliverables we have basically, or this is phase 2 deliverables, we're basically going to develop the method for how we're going to be doing the drop test, affix the accelerometers to the vehicle in order to get the different accelerations in the front and in the back of the vehicle. We're going to, of course, conduct the drop test so we can get those accelerations. Then we had to do some strain gauge research in order to figure out what the strains on the members are going to be, which is going to be part of next quarter. And then we're going to have to, we've been analyzing the data and doing a FEA research and analysis to know where we're going to be pinpointing the strain gauges as well. Here's John with the drop test.
Hey, John.
Oh, whoops.
Whoops. What? There it is. So just the equipment utilized during the drop test. This is the actual shackle, 3/4 shackle that we use. We use a steel plate, and we milled in a 3/4 groove to actually put in for the shackle. This is for the actual drop test, or for the system, the quick release system that we used. We used plastic coated steel braided cable. This was to actually pull the pin out from the shackle. There it is. We use 1,500 pound rated rat straps. These are already here, courtesy of the Baja team. God bless you. We use all-purpose sand. These bags weigh about 50 pounds each, and this was we utilize these bags to mimic the weight of a person inside the vehicle. In total, we use 200 pounds. Next slide, please. We also utilize a Bobcat S630, 74 horsepower diesel, and mainly what we were concerned on, because the total weight was 600 pounds for the vehicle, and that's what we needed, and the rated operating capacity was 2180, so it was perfect. Next slide. Preliminary validation measurements. We weighed the vehicle with bathroom scales. Front left at 201, front right 200, left rear at 211, and right rear at 196. Not bad. And validating the quick release system, we did inside the lab. We used the I-beam, which was rated enough for the car, and we did achieve what we wanted with the system. Next slide, please. This is the accelerometer placement for the front and rear, and we placed each phone for each axis for the X, Y, and Z. Next slide, please. The actual drop test. This is a picture with me actually showing the side view with the shackle. We actually used a cradle mount, so when the pin actually came out, it caught it, so we didn't have to worry about that. And then during each drop, we made sure that we verified that we had the 2 foot between the ground and the wheel before we dropped each time we dropped the car. Next slide, please. This test, each test was done 3 times. At 30 degrees, we did a front, a rear, and side-to-side at 30 degrees with the 2 foot clearance on the same. To measure the compression of the vehicle each time it fell, we used a metal rod taped to the side of the vehicle, and it would actually, when it dropped, pull up, and then we measure the difference between it when it was measured before. That's how we got the compression of the vehicle. Next slide. This is a summary overview of the drop test, just to restate kind of what we went through. All materials and system builds were achieved on campus. All potential safety hazards and risks were discussed and allocated in all parties participating in the drop test. The drop test was conducted to achieve the forces that were subjected onto the car when it was dropped, and that's what the whole point of the drop test was. And Isaac with accelerometers and lab using. Isaac?
So, as John explained, we put 3 accelerometers on the car, on the front tire. This was the Z-axis, the Y-axis, and the X-axis. We did it by the right-hand rule. The Z-axis, the X, and the Y. And this is how the DAC looks like, and this is how the placement of the axis were connected through the wires to the car. This was the USB cable that connects to the DAC, that connects to the computer. That was the power source. And these are the channels, starting from 0, 1, 2, and 3. And the 0 was the x-axis, the 1 was y-axis, Z was 3, and the center of gravity, or the driver's seat, was the last one. Okay, and in our lab, Jake, he specially built this block so we could actually test out how the accelerometers are reading. So he actually super glued the accelerometers to the block, and we did actual testing in the lab by dropping it and seeing if the accelerometers gave us readings. Okay, so next step was to use LabVIEW after we got the reading. So basically I'm going to explain how we use LabVIEW. So when you open LabVIEW, the first thing you see is a blank IV, a VI, which is virtual instrument. And then when you click on it, you can basically get 2 screens. One is a block diagram and the other is a front panel. Okay, on the block diagram, when you take a right click, you get this option, and from that option you click on Data Assist, and then you go to the next screen. On the next screen, you get those options, and from that you go to Acquire Signals, and then you go to Analog Input, and now we're looking for acceleration, so we click on acceleration. When we click on acceleration, we get the next step, which shows us all the channels. And I explained earlier, all the channels, the X, Y, Z, and the CG are lined up. And then you pick a channel. When you pick a channel, this configuration page shows up, and it shows you the max, the min, the sensitivity, the position mode, and the rate, and other kinds of stuff. And these are the changes we made because we were looking for the max. Our accelerometers, the maximum Gs they could read was 50 Gs. So we made our max to 50 and our min for negative 50. And we set our sensitivity to 99.4 because we get from the manual that we got with the accelerometers. And the acquisition mode, we changed it from end samples to continuous samples so we can get continuous samples. And we changed the rate, the hertz, from 25K to 2.6K. And after that, you press OK, and then it builds you a virtual instrument. Okay, and back to the data assisting on the block side of the page. And this was, and then when you do a right click on the right side, we come up with that, and then you click on the graph, so you get this small thing, small pop-up. It's called waveform graph. And when we drop down this menu and we connect data to the waveform by using the pointer. And then you run the program, which is on the top of the page. You run it, and it runs. And this is the time when we actually drop the car. And then we stop it 10 seconds after everything is stable. And when it drops, this is not the actual readings we did, but this was one of the examples. So when it drops, it gives us an acceleration. And the next thing you do, you go into the options, and you go into the logging, and you save the data as a .tdms file in wherever you want. For example, we did it on the desktop. And then from that, when you open it, it opens into Excel. And in Excel, you get a bunch of acceleration readings, well, like around, for example, this gave us 153,601 readings. For that, we used the this function, this command in Excel to find the max. We selected the first column and then the last column, and then we got the max number. And same for the min. We selected the first column and the last column, we got the min.
All right. So after we gather the data from LabVIEW, the next thing we need to do is we either in Excel we make the graph based on those numbers, or we can run through MATLAB, and we window on the event, because when we turn on, there's a time delay between on and when we actually pull the pin, and sometimes it took multiple tries to pull the pin off. So the whole event might be 20 seconds, but the actual drop is only like a second. So we window in the event to the second that the drop actually happened, and then we take that data, we turn it into an ASCII file, and then we put it into MATLAB, and then we filter the frequencies in MATLAB, and then we generate the graphs. Can someone help me with this? So here's the first response. So so we put accelerometers in the XYZ axis, but this is just from the Z axis. So this is a 2-foot drop with a front suspension when it's flat, and the max G is 52. Next. Oh, I need to get this. Next. Next one. So here's the rear raised 30 degrees. So when the rear is raised 30 degrees, the front tires are still 2 feet off the ground. So whatever side is raised at an angle of 30, and then the wheels, the side that's not raised is still at 2 feet. So here is the rear raised 30 degrees. This is still the front suspension, and the max G is 52.4. And this is the right raised 30 degrees, and the max G is 33.7. This is the left side raised 30 degrees, and the max G's is 41. The max filter G's is 41.2. And this is the rear suspension, level to ground, 2 feet off the ground. Max G is 40.3. This is the rear raised 30 degrees, and the max G is 53.4. This is the right raised 30 degrees. Filtered max G is 28.6. This is the front raised 30 degrees, and max filtered G is 27.1. And this is the left raised 30 degrees, max G is 44.1. So this is a summary of all the G's that the car sees during the testing. So when we dropped it 3 times each test, and this is the greatest acceleration it saw from those 3 tests. All right, next is Eric.
Oh, no. Slide? Okay. Okay, so I was in charge of FEA research. What we want to do is we want to get our test results and create an FEA model on SolidWorks and actually compare our stress values and see if we're within 50% of the difference. By knowing the stress of the suspension seats, we could either develop the A-arms either to be thicker or lighter, but still be able to survive those stresses that we see. Okay, so for the first 2 weeks, I thought I had it, but our plan originally was to create a drop test using SolidWorks. In the drop test, we needed to create a frame. So what we did, we actually measured each point of where the weldments are stick together and get the X, Y, and Z coordinates. We put that on Excel, and then when I did transfer that Excel file into SolidWorks to get all these points. At these points, I just connected the dots, and we found that we made a general shape of the frame, and we got the suspension points where they're located, and the shocks. Next slide. So first, the drop test for SolidWorks is very picky. It took me a while to get this frame because you have to, each weldment here, when you have too many tubes there, it creates interferences, and when you actually try to simulate the rods using the mesh, solid meshes, the drop test just doesn't like it. So after a while, and we had to also include the shock in it, but in the drop test simulation, we cannot give our shock a string stiffness. So we had to get this idea. I just wasted my time and had to throw this simulation away and start with the new plan. The new plan was to use motion analysis. Next slide. So pros and cons of motion analysis. In order to assemble all our parts in the assembly, we could use mates, which is better than the fixed geometries and actually applying the forces. And we could also, when we were meshing and running FEA, we could choose certain parts. For example, like if we do a static test, we would have to mesh the whole A-arms, kingpins, the tires, the wheels, and that's just a waste of time. So in motion analysis, we just pick, okay, we just want to find the stresses on the A-arm. So we just pick those two A-arms and create a mesh and run the simulation. Also, another neat thing was time dependent. So we actually have, we could assign the time for like 0 to 5 seconds and actually run the simulation and see how the suspension goes up and down. We also get to see a real-time animation of how it moves. Some cons. We don't have very much control over our results charts, and we don't get to use a probe tool to select certain nodes and see which node has the max stress. Next slide. So first, we had to find the spring constant on our springs that the car has. We got this spring compressor. We compressed the springs so we could actually take the springs out and measure the stiffness. We did this by calculating the initial length with no weight on it, and next we started adding weight until we saw it compress 1 inch. For the black spring, we saw that it takes 131.01 pounds just to compress 1 inch. So we could, that will be our K value for the black spring. Also, you can see the top picture, we have both springs in series. What it means to be in series is that when you compress it, they both have different displacements. Can you go to the next one? So to find the equivalent, when you have two springs, to find the equivalent spring constant, you have to use this equation, 1 over K equivalent over 1 over K1 and K2. After you do a little bit of algebra, you find your KQ using that equation. So our K1 will be our yellow spring from the previous slide. Our K1 found for the little spring was 301 pounds to compress 1 inch. For the black spring, we found that the spring constant was 131. So when you plug all the numbers into the equation, we find our K equivalent is 91.31 pounds per inch. So in order to make sure that we're actually doing this right, we created a little FEA model of the shock and try to compare our values. So for springs in series in SolidWorks, you have to create two faces. Choose two faces for the top spring and two faces for the bottom spring. For the top spring, that will be our black spring, that's 131 pounds per inch. And the bottom string was the yellow one. SolidWorks creates the equation by itself and actually solves this and already knows your K equivalent without you having to input your spring constant that you found using hand calcs. So during our hand calcs, we found that it takes 91.3 pounds to compress 1 inch. That's the force I applied to my FEA model, and as you can see, the results we got was 988,336 microinches, which is around 1 inch. So our hand calcs are pretty accurate. Next slide. So now we move on to the motion analysis features. As I mentioned, we have time dependent, so we could actually choose which time we want to analyze, whether it's like 0 to 1 seconds or even more. We also have the options to include a spring, and to include the spring, we do the same features as the other slide. We choose two faces on the spring, the top and bottom, and then we give it a spring constant. We also have a force, which is the force we got during our testing, and we're gonna apply it to the tire. Another feature we have is contact. So since this is an animation, when you apply the force to the wheel, since nothing's holding the wheel in place, you're actually gonna get the wheel moving. So you have to tell SolidWorks that when the wheel's moving and it hits like the A-arms, to stop it there. That's what the contact feature does. Also, when our shock compresses, if the load's too much, it might go through it, so we need to add a contact between the top shock and the bottom shock. The little green apple represents gravity, and then we have the other three tools, one with the little rainbows. That's our FEA analysis tools. Next one. Okay, so since we're doing a static test next quarter, we're planning on applying our force using the jack, and that jack's gonna have a little like weight, like circular weight, so we could actually apply the force. And I try to kind of mimic that face and actually create a split line. So when I apply my force, I apply it at that face. And the blue arrow represents the direction of where we're applying the force, which is up. Next slide. So then I just ran this quick example to see if I was getting like the right results. So using the color shot, the picture, we can see different colors, different stresses, and you can see here the green stuff. We get like some stress around 228 psi. We can also use these to get an idea of where to place the strain gauges. But the thing with this, that we cannot adjust this chart. For example, like I see red, but there's no red here. In reality, there's probably like little pieces of red inside, but we don't have control. Because in other simulations, I could give it like, let me just see stresses from 0 to 300, and that changes the whole color, and I could get more accurate readings. Also, I cannot use the probe tool as I mentioned, because the probe tool, what it does, if I see max stress around here, I just click it, and it tells me what stress I'm seeing at that point. We don't have that option either, so kind of getting those numbers are going to be a little more challenging. But the thing we could do is estimate our location. So I could actually edit the sketch, add points here, and then using the measuring tool, just measure the distance from here to here, and get an accurate reading of where I want my strain gauges. That's it.
Okay. So basically, the summary of the whole project is that we've developed a drop test in order to figure out what the accelerations are going to be on the vehicle, and with the accelerations, we could then determine what forces that vehicle is going to see also from the testing. When we know these forces, we can now do our static test, input the forces into the jacks, and we'll know exactly what forces we're going to be applying into the tires. And what we're going to do is use a force transducer in between the jack and the locations where we're going to put the forces on. That way we'll know exactly what forces we're inputting. From there, we're going to have the strain gauge locations on the various arms of the vehicle, and we'll be able to determine what kind of strains it's going to see also at those different locations. So basically we have a handful of different risks that were possible to happen during these tests. They range from injury, breaking the vehicle, damaging instruments, breaking the forklift, and then the LabVIEW code's not working as well. We figured out various ways to mitigate those risks, and for the injury it was basically one person's in charge of the drop test at all times, and that person's calling all the shots. For the breaking the Baja vehicle, basically we determined instead of just going to the initial 3-foot height and dropping it from there, we were going to do incremental drops in order to make sure that the vehicle wasn't going to completely break over a foot or at higher heights. The damage to the instruments, that's not really too much we could do about it. We just basically followed our safety procedures and our test procedures to make sure that we did everything as safe as possible. And then the forklift, we weren't really too worried about damaging the forklift, but we just always basically made sure when the vehicle dropped, especially at the angles, that when it dropped it was going to fall away from the forklift instead of falling and then bouncing towards the forklift as well. And then the LabVIEW codes, basically what we did for those is we tested the accelerometers before the actual drop test to ensure that we were getting results and readings out of them as well. So here's a basic chart of the consequences of the risk versus the probability of the occurrences. And there were a few of them that were a little bit in the yellow area, which had some basically some possible disruption. I don't remember which one was in the orange, but basically we didn't really run into any problems with the whole program and with the drop test, and everything ran really smoothly for us. Any questions?